I guess one of the biggest differences, one of the biggest changes between Raspberry Pi 4 and its predecessors and Raspberry Pi 5 is imaging, is how we deal with data that comes from the camera. Now, we've been doing cameras at Raspberry Pi since about 2013. I think we had a 5 megapixel Omnivision product, which was actually the very first official accessory for the Raspberry Pi. Back in those days, how did we deal with data that came in from a camera?
Well, back then, it's important to understand that these are what's called, they're kind of called raw sensors. So you get sort of a very basic form of pixel data from it. It's not sort of beautiful, nice images that you can just sort of throw straight on the screen. So they need a lot of processing to make them look nice. So we get these very raw numbers. They come off the image sensor.
And these are red, green and blue values for every pixel?
Not for every pixel, no. In fact, every pixel actually only has a single color, in fact, and then part of the processing that we have to do is to, well, we would say interpolate the missing colors. You could say invent, perhaps, that will make up, I don't know, the missing colors. So that's one of the things that happens. But anyway, so you get these pixels coming off the sensor. They come down on the Raspberry Pi. People will know the flat ribbon cables that we have. So they'll come down the ribbon cable. And there's a hardware block on the Pi that receives them. That's called the receiver, and which just dumps them into memory is all that happens. They just get dumped straight into memory, and then everything else happens actually on the main chip itself. And there's this piece of hardware which is called an image signal processor, often abbreviated as an ISP. So nothing to do with internet service providers.
I'm super excited to learn it is an image sensor pipeline, which is what I always kind of thought.
Well, it used to be. It's changed names.
Right,
I think most people, yeah, it's had various versions of the abbreviation, but I think most people now call it an image signal processor, I would say. So there's one of those on the Raspberry Pi chip.
And this reads these bad images.
Yeah.
So these cameras, they're quite cost engineered.
Yes.
Aren't they?
Yes.
So both the optics and the sensor itself.
Yes, that's right. Yeah. So then as we've said, the pixels that we have in memory at this point are quite ugly things. I mean, they're dark, they're gloomy, they're all mostly green. It's just a bit of a mess, really. So you can't use those for anything really. And then there's this thing called the image signal processor, or the ISP, that reads everything back from memory where it's been stored when it arrived from the sensor. It processes them. It does lots of stuff to them. We can talk more about that in a minute, I guess. There's lots of stuff to them and makes a nice picture. And then writes that back out to memory. That's basically what happens. So it's just dealing with processing the pixels into a nice output image. There's no image encoding, so it's got nothing to do with image encoders or JPEGs or anything like that. That's
so this is
later.
This is RGB data coming in from the camera.
Well, it's called
Bayer data. What's Bayer data?
It's one red,
right.
one blue, and 2 green pixels.
For each little 2x2. So this, when you say each pixel only has a single color, that's what you mean. It's either red, a green, or a blue, and there are twice as many greens as there are the other colors. This data is coming in as Bayer data, which is this kind of sparse RGB data. It's going through the pipeline. It comes out as RGB data, or does it come out as something else?
RGB or YUV.
Right. Okay.
Yeah.
And so YUV is another color space. It's this kind of intensity rather than just saying this much red, this much green, this much blue. It's kind of this much brightness and this much color.
Color difference.
Yeah, color difference.
Yeah. It's a different color encoding, I think we would say.
It's optimized for video encoding.
Right. Right. And that would be then the encoding of something like video encoder or JPEG or JPEG users. Okay. So if you're going to take your data and store it, encode it and store it, it's more convenient to have it as YUV than RGB.
And YUV allows you to compress not compress, but remove some of the color samples.
Right.
Because.
And why is it safe to do that?
Because your eyes are more sensitive to luminance changes than color changes.
Right. This is rods and cones. This rods and cones density.
I mean, you could argue it's not terribly safe to do it, but we do it anyway. I mean, it does.
Well,
everybody does it.
It does create problems. I mean, that's one of the reasons why when you see people with highly stripy shirts on TV, sometimes you get some funny colours appearing. and that's because they actually throw away the color data, right? That's why it happens.
So, so that's the classic world where you have 2835 on a Raspberry Pi 1, 2711 on a Raspberry Pi 4, and all of that's integrated into one chip. So you have the receiver, you have the block that writes data from the receiver to memory. That's called Unicam in the old world, right? And then you have the ISP, the image signal processor, which is a memory-to-memory busmaster, which is pulling those Bayer images in, doing stuff, and then writing either non-sparse RGB or YEV, or non-sparse YEV or subsampled YEV back to memory. So we should probably talk a little bit about the stuff. What did stuff consist of classically? Obviously, one of them would be D-Bayer, right?
So, yeah, I mean, statistics, black level correction, D-Bayer, as you said.
I mean, we generally start off trying to fix defects in the image by trying to reduce the noise and to spot defective pixels. Although actually the sensors usually do quite a good job of hiding defective pixels themselves, because the sensor manufacturer knows what kind of defects are likely to be present.
Right. And so you may just, in a 12 megapixel sensor, you may just have some pixels which are dead.
Yes, and you just replace those with the neighbouring signal.
Right.
So really the first thing we try to do is get rid of noise by smoothing where the image looks like it ought to be smooth.
Right. Okay. So this is, and what sort of noise is this? This is thermal noise, or?
There's thermal noise and quantization noise in the electronics. There's also shot noise due to the fact that the photons arrive at random times.
Right. So you're trying to kind of build some model of what you think is of what you think the signal should look like, and then kind of push the signal towards what it should be like.
So there are different ways of doing it, but the general approach is where the signal looks like it's smooth up to a certain degree of noise, you make it more smooth.
Right.
And where it looks like there are sharp edges, you kind of preserve it.
Right. Right. And that's spatial. So that's spatial denoise. Okay. So you've done some spatial denoise. Then what? You've got distortion correction in there somewhere?
Yeah. I mean, I was going to take a step back actually and just say they're kind of. To my mind, there are two kinds of things that we tend to do. There's the sort of large-scale processing that we do to images. So this is about getting the colours right, getting the kind of the gamma curves right. So the thing basically looks like a nice image, and you can kind of think about a lot of that without worrying about the actual pixel level detail and all that kind of stuff. But then that's the other thing that you have to do. Obviously, you have to get the pixel level stuff sorted out as well. So this is always very sort of fine-grained. It's to do with the denoising that we've talked about. It's to do with the sharpening. It's to do with debayering as well, all those kinds of things. So there's very much these two things going on.
Right. And you have a pipeline of these. You have a pipeline of these stages, and you're passing. Right.
Operations.
Right. And you're passing pixels down this, and it gradually becomes. You start off with this Bayer, extremely incorrect data, and at the end of it, you hope to have something which I guess is true for some value of true, is the closest you can get to the ground truth, the actual state of the world that generated the.
Yeah. I mean, yes. I mean, I'll go on to say that a lot of the sort of corrections that we do. So Nick talked about the defective pixel correction, the denoising, all that kind of stuff. You try and do it early, because when the pixel numbers that come off the sensor, I mean, you have some expectation as to what statistical distributions they follow and this kind of stuff. You probably calibrated and measured them. So you kind of do stuff with them. As soon as you started touching the pixels and doing stuff with them, all that starts to go away. So you kind of can't do that anymore. You can't denoise as effectively later in the pipeline because you've done all kinds of stuff to the numbers. So you kind of got no idea really what you're looking at anymore. Right. So a lot of that sort of stuff happens early.
So there's a natural order.
Yeah, there is a fairly natural order for a lot of it. You try and do a lot of that sort of stuff early. You fix up the problems, and then you've got to sort out the colours, the transfer function, sharpen it up a bit, all that kind of stuff.
So the big sort of milestone in the pipeline is demosaic, where you're changing. Before that, you have the Bayer order data, and after that, you have RGB.
Right.
And after that, you also have to gamma, which then removes more linearity from the pixels.
Right. So that's your kind of classic ISP pipeline as a memory to memory master. You then have You then have things that kind of algorithms that kind of run around the outside of this, the sort of 3A stuff, is that right? So these are your auto
So
algorithms.
auto white balance, auto exposure gain, and autofocus. But these days we do another one. We call it 4A, don't we?
Yes. I mean, the way to think of it really is that every block in the hardware, we have an algorithm associated with it pretty much. I mean, that controls it. Some algorithms control more than one block. So a typical one would be, we talked about the auto exposure and gain algorithm. So that would control, well, that controls the sensor, but it also controls the gain block in the ISP. And then other blocks, like there's a block that applies color gains, that again has an algorithm that controls it, happens to be called the auto white balance algorithm. So every one of these algorithms.
And your auto white balance algorithm is so your automatic gain control, automatic exposure algorithm is trying to avoid the image being blown out. If you walk from inside to outside, something's going to happen that causes this outer set of algorithms to say, too much light, dial down some gains, and if you walk back inside, you go, well, this image looks almost black, let's dial the gains up a little bit. Similarly with the color, I mean, I saw an amazing, the New York thing, I saw a really wonderful thing recently where somebody, they had the orange sky, all that dust that had come, and there was somebody illustrating that smartphone pictures of it weren't really capturing how incredibly orange it was, and they took one of the color charts outside and then calibrated because the auto white balance was trying to was saying, well, this image is too orange, let's make it less orange. And then when you take a color chart out and say, that square there is white, drive your auto white balance from that square, suddenly you see how incredibly orange the place really is.
Yeah, I mean, that kind of thing is actually classic because, I mean, auto white balance is kind of an impossible algorithm because when you're looking at a white wall under a kind of yellowish light, you can't tell that it's not a yellow wall under a white light. You have no, so it's a sort of it has like statistical properties. You have to look at the sort of statistics and likelihoods of the things that you're seeing and determine what you think is most plausible. And so the upshot of that is, of course, that white balance algorithms tend to be calibrated against typical scenes so that you assume kind of normalish behavior of things. And so when you get sort of exceptional circumstances, they get caught out. So that's exactly it. And the trick is to, cover as many of the outlying circumstances as you can without messing up the kind of common ones as well. But
So and then the other classic algorithm is autofocus, where you have one of several methods. And with camera module 3, we've got several methods, including the phase detect method for going, hang on, this image is this image is out of focus. Drive the focus actuator backwards and forwards.
yeah, so the camera module 3 uses phase detect autofocus. I don't know if Nick can tell us about that, but it's a particularly cool method actually of doing autofocus.
The nice thing about it is you can't, as well as telling you whether it's in focus or not, it tells you which direction you have to move the lens to get it in focus.
Because there are simpler contrast detect autofocuses, aren't there, which try to kind of maximize it. When it's out of focus, it's blurry. So if you make the image have more high frequency,
You have to search for the lens position that makes it least blurry.
Yeah, and that's very difficult because you have no definite knowledge that it's now out of focus. There's something wrong. All you can do in that kind of world is just, well, the image has vaguely changed a bit. Maybe I need to do another autofocus kind of search, and you don't know whether to go forwards or backwards. So you get this kind of hunting behavior, and it's very hard to calibrate it to hunt for focus only when it really needs to. Rather, it's basically it's impossible. It's a big
But
trade-off.
the phase detectors.
But the phase detect nails all that for you. That's why it's very common now on all the cameras.
So you've got ISP in the middle. You've got receiver. You've got Unicam, receiver, ISP, algorithms that are inside the ISP. But we talk about tuning sometimes. What is tuning?
It's all the characterization of a particular camera. So it's everything from you calibrate what kind of noise you get from a sensor, so that the hardware block can be told what kind of levels of noise it has to sort of try and flatten. You calibrate the color response of the camera so that it knows how to turn the camera's version of colors into like proper, true colors that you would recognize. What else?
Lens shading?
Yes.
Shading correction,
Yeah, so vignetting and color shading, very common across lenses, all that.
Gamma, how we shift the luminance in the image to make it look nicer.
So you end up so the flow there is you get a sensor or some set of sensors, some representative sample of sensors from the manufacturer, and then you take pictures of some known stuff, and you derive from that a big table of numbers which constitutes the tune.
Yes.
And that's changed a little bit, hasn't it, over the course between the old world. There's not just an old hardware world and a new hardware world. There's an old software world and a new software world, right? So the lib camera world tuning is a little bit different.
It's a lot simpler.
Yeah.
A lot less numbers to deal with.
Yeah. So there's a lot of configurability in the classic ISP, and you've found ways to really kind of slim that down to just the meaningful configurability.
There's various things we've done. I mean, in the old world, again, we had lots of different customers, and they tended to be often quite big customers. And when they wanted a particular feature, you would give them the particular feature they wanted. But it sort of meant we had piles and piles of features for every customer we'd ever worked with. They wanted particular things, and so this thing filled up with numbers like crazy, really. It made it very hard to create. I mean, this is one of the reasons why the HQ cam took so long to roll out, because my goodness, someone had to make this tuning file up, and it was just a nightmare. That was you. That was not. So that was really hard. So we were very keen. Yeah. So we were very keen to drop all that stuff that we thought just wasn't really useful, generally speaking.
Most of those numbers you wouldn't touch.
Yeah, and to some extent in the new sort of open world, where people want these kinds of particular behaviours, they can put them in. The code's there, they can do it. So we didn't feel we had to put everything in off the bat. But then there was also a real wish to make the whole thing just a darn sight simpler, so that we could turn a new camera around in a few days or something, rather than like months every time.
So you had these big tuning campaigns for OV50-647, which was the camera module 1, IMX 219 for camera module 2, 477 for HQ cam, and then the lib camera world appears and subsequent cameras. So you then went back and retuned tuned those old cameras in the new world. Yeah. So you can still use a camera module 1 in the lib camera world.
That's right.
But the subsequent cameras are only tuned.
And we think it looks better.
Yeah.
It mostly looks better, and we have a much better handle on what's actually going on inside it now. It's a much.
I've seen some really nice camera module 1 pictures recently that are materially better than I would historically have thought camera module 1 could do.
Yeah, I think we do better even on the old platform. Actually, the tunings that we have are better. But just in part, they're less complicated, less of a nightmare to make. It means we can spend time just getting the basic things in order, and it's a much better place to be.
So that's the classic world.
Yeah.
That's the classic hardware world. What's different in Raspberry Pi 5?
I guess the main difference is it's been split between 2 chips. So the CSI receiver and part of the ISP are now in the RP1 South Bridge. And then most of the ISP is in the main processor, 2712.
So you have MIPI, and we have 2 4-lane. So we've grown some.
Yes, we have 2 4-lane MIPI ports that can be either CSI2 or DSI, or one of each.
And we have a little bit of a challenge finding 4-lane. There aren't a huge number of 4-lane sensors, obviously, but.
All our standard cameras are still 2-lane,
But the door is open to start doing 4-lane ones.
And there are some super high resolution 4-lanes.
And we'd love to do it.
that would give us much higher resolution and higher frame rates. Yeah.
It'd be great to do. I mean, the HQ cam in theory will do 4-lane.
HQ camera can
I mean,
do 4 lanes.
there's obviously a lot. We need a board that has 4 lanes. We'd need a driver that supports for all these things that we don't have now. But the door is open to doing these things, and then we could just drive one of these things at 12 megapixels.
Or two of these.
12 megapixels, 30 frames a second.
So you have 2 camera connectors. Each of them is twice as wide as before. Yeah. And as you say, these are not connected to the main chip.
They're on RP1, yes. Right. And then co-located on RP1 with each of these MIPI interfaces is what we call the ISP front end, which doesn't do a great deal. One of the significant things it does is get statistics early on the raw image coming in. Right. So we don't have to rely on feedback from the previous image. We've got more data up front.
Does this make some of these 3A, 4A algorithms easier? Is that what?
Yes, I mean we can converge a bit faster.
Right. It removes a bit of the latency.
So you're doing some early processing, a little bit of defective pixel work?
There's defective pixel correction. I don't think we're using it at the moment. As I say, the sensor manufacturers tend to do a good job, but it's there if we need it. Right. That's really there to protect the statistics. Right. And there's also optional downsampling in the front end to reduce the memory bandwidth.
I think it's probably more to protect the downsampling, actually, isn't it?
Yes.
I mean,
Once you start messing with the image, then the pixels become correlated and it's harder to do defective pixel correction.
And one of the things we do in the front end is we also compress.
And we have the
data.
compression scheme.
And that's a lossy, slightly
It
lossy.
is slightly lossy. It's 10 or 12 bits down to 8 bits.
But
it's-
only a little bit of loss.
You couldn't
It's been carefully designed for our use case to try and make it so you can't see the loss.
Because we have a relatively, well, we have probably what in my mind is a lot of bandwidth over PCI Express. We have 2 gigabytes a second of bandwidth over PCI Express, but this is in a platform that has 16 or 17 gigabytes a second.
But it's also on the other end.
Yeah.
So when you're reading in from the backend ISP, you're reading in less.
Yeah,
your
I mean,
bandwidth
the
reduces
thing,
there as
yeah,
well.
I mean, it's just sort of for everyone listening, it's worth putting out that it's optional, the compression, so you can turn it off.
Yeah. Is it turned on by default?
We do mostly turn it on.
Yeah.
Yeah, we do most, but it's optional. You can turn it off and not have it.
But if you want to be able, so in the future where we potentially do have 4-lane, a pair of 4-lane high-resolution cameras connected, of course, yeah.
Yes, then we'd appreciate having
That'll be
compression.
very helpful. Right. So that stuff is in RP1.
RP1,
You've then got-
statistics, compression and a bit of downscaling and defective pixel correction. And then 2712, we've got most of the ISP.
Which again is a memory-to-memory master, so it's now reading the potentially compressed, somewhat touched up data that's come in over PCI Express from RP1, doing stuff to it, and getting nice pictures out of the back. What stuff? How's the stuff different? So a lot of the stuff the overall shape of the stuff is quite similar, right?
A lot of it is very similar. I mean, I would say, one big difference to start with, it's got much higher throughput. And that's a huge change. I mean, it's clocked higher and it runs at 2 pixels per clock.
Right.
So, I mean, this.
I think it's clocked at something like 800 megahertz. Right?
Yeah.
So you can get 1.6 billion pixels a
yeah.
second.
I mean, this thing will do dual 4K P60 in its sleep virtually.
Right.
I mean, it really is very capable.
We've gone from sort of single pixel per clock, 500 megahertz, to 2 pixel per clock, 800 megahertz. So it's over a 3x uplift.
Yes, that's right. Yes, I mean, in reality, the old ISP, you got 200 or 300 megapixels a second through with a bit of luck. Would you say?
Yeah, you remove about, you have an overhead of about 30-40% because of the overlaps on the tiles.
Right.
And similar here as well, but not as much overlap actually in the new world. But yeah, so you'd get about 200, 250 megapixels
but
per
as I say
second.
now, it's vastly greater. So throughput is a really big difference.
Yeah. And in terms of algorithms, some of it's better versions of the same thing, right? Better debayering, better spatial noise.
Yeah, I would say the spatial denoise is certainly better. It's got the filters have kind of wider support, so you get better performance that way.
What's
temporal
actually
denoise?
So that sounds like the big. So when we talked about denoise, we talked about spatial denoise, about looking at a pixel and looking at its neighbours and going, yeah, that doesn't look right. That's a smooth. There's some smooth change that I can see across my filter support. I can see some smooth change, and this pixel is sticking out above that smooth change. It's probably not a real edge. It's probably shot noise or thermal noise. So that's spatial denoise. But now we have temporal denoise, right?
We do. So there's fully hardware temporal denoise. So what this does is it compares every frame that arrives with kind of the previous frame, effectively. And if where they look like they're the same, it sort of averages them together in some way. But this is a long-term process, if you like. So it's all the while it's kind of averaging frames to create what we call the long-term average frame. So this is kind of like the temporally denoised version of the frame. I mean, every time a new one comes in, we compare it with that. And we kind of merge them together, and that's the new long-term average frame, and that's what then goes forward down the rest of the pipeline.
So sort of looking behind me at this blank space behind me, if in a video there's variation from frame, significant variation from frame to frame in that colour, it's obviously wrong, right? Because it's a static thing, it's not changing, and that's what temporal denoise tries to capture.
Yes, it will really clean that sort of stuff up.
Yeah.
So you get much lower noise videos. You get to spend much more of your bit rate for your encoders. You actually spend encoding the detail and not the noise. So you get much better video quality as a result. So temporal denoise is a really good feature actually to have. I mean, things get much cleaner, and so that's nice.
It makes a tremendous difference. When you see it.
So is that the big ticket in terms of things which are qualitatively different about this ISP?
Yeah, well, yeah.
That's one of the big things.
One of
definitely.
the
Yeah,
things.
yeah, one.
HDR is another one.
HDR
HDR is the thing we've been looking at, yeah. So again, there's various ways you can drive that. You can.
So sorry, what's HDR?
So high dynamic range imaging. So normally what this means is you have to have several images and you have to combine them together in some way.
So exposure bracketing.
Yeah, it's a bit like exposure bracketing. So you get both the dark areas, you can bring them up, and also the highlights, you can avoid them blowing out and try and bring them down.
So it's sort of the classic room with a window,
Yeah.
badly lit room with a window,
Yeah.
where you want to somehow simultaneously have not much gain, so you can see the tree out the window and the window doesn't just blow out to white, but also quite a lot of gain inside the room, so you can actually see things in the room.
And our camera module 3 does this on chip. But now we're going to try and get the ISP to do it for the other sensors as well, or any sensor. That's kind of fun.
Yeah, so that is quite fun as well. And there's various different ways we can drive the HDR processing.
So is this a commitment to bring HDR to HQ Cam then? Or?
Well, I mean,
At least for relatively static scenes.
well, yeah. So okay, it's all complicated. There are two kinds of HDR that we're doing at the moment. One of which is where we basically run the camera underexposed and combine all the frames that come in. We basically kind of add them up and average them. So it's kind of like we had both short exposures and long exposures, and we kind of munge all those together, and then that goes forward and goes through the tone mapping process. So actually that's quite a nice form of HDR. It's very good for video actually.
Yeah, because you don't suffer motion artifacts.
We don't suffer motion artifacts because it basically relies on temporal denoise to sort of basically add things up. Is kind of what it does.
So how does it get rid of motion then? If
So
global motion or local motion?
Yeah. So what happens is that because temporal denoise averages where things are the same, and where things aren't the same, it just takes the most recent frame that's just arrived. So kind of
you kind of
things
lose
are
your
moving.
HDR for moving objects, but
So you have the HDR, but what happens is you get slight kind of noise halos if things are moving. So you still get a perfectly reasonable picture and it's all good, but where it moved, you get a slight halo where it's a bit noisier, if you like, but it's a fairly marginal effect. But the rest of it all, you can run this whole thing at 60 frames a second or whatever, and it's quite nice. Then there's another form of HDR that we're doing. This only really works for still scenes at the moment. There's kind of, a lot of this stuff is, I would say, it's a bit of a first cut, some of this stuff. There's a huge amount of new stuff, obviously, regardless of the fact that, the whole thing is new. But there's lots of new stuff we developed for it as well. And so there's this other form of HDR where you actually get long and short frames and it actually combines those directly together. And that, I would say, is more for still images at the moment. So there's a slight work in progress on that one. It's not so good on moving images because the artifacts aren't compensated so well on that. But yeah, that's work in progress. So, the next version, whenever that's going to be, will be perfect.
But lots of this stuff is there in the system already and is latent. And so we're kind of opening up, and I think this happens with every major revision of the platform. We talk about kind of like the major revisions of the platform are like steps, like treads on a staircase, and then it's like in between the software work, you kind of pour sand on the staircase, and you get sort of a gradual improvement driven by software. And then really what's happened is it's increased the ceiling on what you might be able to do in software.
Yes, and I think as time goes on, some of these things we'll be able to do a bit better, particularly if. Not always some, if you're doing 4K video, 4K P60 video, it's kind of hard to do very much in software just because there's so many pixels flying around. But if you're doing still image capture, actually there's quite a lot of scope for adding some software processing and that kind of thing to improve some of these areas that will then improve in hardware again later on another revision. So there's a whole kind of path of stuff happening there, because the ARM cores on this thing are,
pretty powerful.
They're stonkingly good. They really are.
Yes. I just ran the numbers last night actually, and I think we have something like, if you compare the GPU on the platform with the CPUs on the platform, you have about 50%. The total floating point throughput of the ARMs is about 76 GFLOPS, and the total throughput of the GPU is about 50 GFLOPS. So there really is, or mid-40s even maybe. So there really is a huge amount of performance available to you there on the ARMs.
Yeah. I mean, the thing I always come to is the most exciting thing about this platform. I mean, all these things that we've got there, whether it's temporal denoise and HDR and better this, better that, more output formats, just more of everything that's better on everything. This is all great, but actually the most exciting thing is that it's our platform and we get to develop it going forwards. I mean, that's actually that's the most exciting thing, because up till now, we've had a platform. It has never changed. Nothing has ever changed about it. No bug has ever been fixed. No material performance improvement, other than a bit of clock uplift, I suppose. But there's been nothing ever, right?
And so this ISP, this new ISP, was developed at Raspberry Pi and then put into the core chip.
It is ours. We're already making plans for the next version of this thing. Some of the cool features that we haven't squeezed into this one. They're going to go into whenever the next one is.
And imaging had become an outlier in terms of the hardware. Imaging had become an outlier that it was the only thing that had not moved forwards. Once we upgraded in the last generation to Video Core 6 for GP for 3D and to Video Core 5 for the scan out for HVS, it had become the only surviving block, maybe video encode as well, about the only surviving block in the platform that hadn't seen some attention since the days of 2708, 2835.
Yeah, so I mean, it's hard to exaggerate what a big deal this is. It's not a step change. It's a whole new building. It's just everything is brand new. But now the step changes will go forward on every time we can find an occasion to do a new version. We'll come to you and say, we want to do this.
Yeah. Get me a new chip.
Yeah, we want a new chip, please.
Look, I have RTL, get me a new chip.
Look, we've got new fabulous stuff. So that's really exciting. Yeah.
Excellent. Well, looking forward to having a play with it. Thank you very much.